Hello, this is Robert Casey, and this is a presentation about how to create your own mathematical YSNP prediction model using the statistics software package called AcaStat. This product is only available for $10 and is really much easier to use than people imagine. This is going to be step-by-step directions on how to use AcaStat. The purpose of the presentation is to show just how easy it is to create a YSNP prediction model. The product only costs $10 download plus taxes, and preparing its two pieces of it. It takes about 5 minutes to prepare an input file, and then also about 5 minutes to run the model and capture the output. However, every time you do test new boundary conditions that are more extreme, you really need to run the AcaStat again, or your model will suffer slight accuracy problems around 1%. This section is to show why you want to do a prediction model versus a table lookup empirical model. Above is the actual empirical model for our L193. And everybody who tests at these signature matches with that kind of distance or less will test positive. This has 0% false negatives because this does catch everybody because it's based on positive tester. But the simplistic model creates 36 false positives of people who tested negative or confirmed tech nesting, but if you use this algorithm, they're positive. So that's going to generate a lot of bad data into your data sets by using this simplistic approach. Here is a spreadsheet that shows the problem for L193. First of all, if you look at the above, everything in green is positive, and you look below, everything is negative in magenta color. So you look at 5 of 10, that's what you have to go down to or up to a genetic distance of 5 to match and to catch those two. But then if you look down below the magenta color, that includes 3 negative testers as well. And those with the model built just on positive tester would give you 3 negative results at a signature match of 5. Then you do a signature match of 4, it goes up to 11. And you look down below and the bottom third of the screen, and it goes on for another 10 or 15 values on the next screen. They all will be falsely predicted to be positive as well. So almost all haplogroups have some kind of overlap, and this is why you really need a statistical model. First, I'm going to assume that you have all your positive and negative testers confirmed and color-coded in some manner, or having a column list of saying 1 or 0. But for AcaStat, you have to create a column, and for all the ones that are positive, you have to enter 1, which is a positive result. And for all the negative testers, you need to enter 0. The 0 testers are required to train the actual model to be able to reduce testers that are negative from being calling positive. So the first thing you need to do is create a new sheet, which is the tabs at the bottom, and label it AcaStat. And what you want to do is you want to copy all the columns to include the FT and AID, and that's really for references only. The results where only 0 and 1 are there, and then the columns with signature and GD. Then you want to paste with values only to convert the formulas and this for signature and genetic distance into numbers versus the formulas that they currently are. So this screen shows you the darkened area is what I'm copying. On column A, that's the family tree and ID number. And then in column H, that includes 1. For when it's green, it's positive, it's 1. And K and L is where the signature. So you have to get them all so you get that information, and you'll delete the extraneous stuff afterwards. Next, this is the actual paste, values only. And if you notice, all the colors go away, because when you do values only, all the formatting goes away. But it does have column A for the family tree ID, H, 1 or zeros, and K and L. This is after you delete all the extraneous columns. I also changed it to Arial font and left justified everything to make it look a little prettier, but you really don't have to do that. That's just a visual thing. So now you have all the data for input as a sheet, but you actually have to have a CSV comma delimiter only file for input to AcaStat. This can be tricky many times. If you follow steps, it works. So with AcaStat, with the AcaStat sheet active, save the file and change the name to include AcaStat input, which is going to be a new name to separate your files and make this an input file to AcaStat only. Note that in column 1 and row 1, if you have I or D and you're on Microsoft either 2003 or 2013, which I was, this will cause a bug. So I had to change ID to family tree and ID so the bug would be eliminated. Then do a save as, go down and do the where it has file type. You use the pull down menu and pick CSV comma delimiter. Now there's two other CSV formats and they will not work. It has to be one that says CSV comma delimited. Microsoft goes out of its way to confuse people with lots of warnings and that kind of stuff. So the first time it comes back, it'll say, give you a warning that other sheets are going to be lost because CSVs do not support but one sheet. And that's the tab down below. And so it will delete the other ones, but you're saving this in another file, and you really only want the sheet that we just created with all that data. Next, it's going to give you another warning that says that some features will be lost. And what that is warning you that all the formatting, such as color, is going to remove because CSV does not support those kind of things. And we don't care about those things, and neither does AcaStat. Also, when you exit the file, and it says, it gives you another thing. It says you need to select Do Not Save because that puts you in the endless loop of trying to save the same stupid file. This is another bug in Microsoft. So now you have created the input file, and that's the 5-minute procedure to create this CSV file. So you next obviously have to download AcaStat. It takes like 5 minutes to install. It'll send you email and use the link, and you can put it up to 3 different machines if you want to. Once you do that, then you gotta launch AcaStat, get the program up and running, and then under the file menu, pull down menu, you select import comma delimited text file, which will be your CSV file. Select that file by going to the directory where the file, hope you didn't memorize where you put it, and then select the CSV file that we just created. Under the procedures pull down menu, you have to use the scroll bar and pull all the way down to the bottom and then do a page up once, and then you'll find the term regression log. That means that's logistic regression, or sometimes called binary logistic regression. This is the model that you're selecting to emulate or to model with your data that you've now input. Next, on the top right, you click on the button called Calculate, and it'll actually go through and calculate it. And it takes less than a second to calculate all the stuff. And then you go to one of the tabs called Output Log. You click on that, and then inside of the Output Log, you want to copy from the bottom portion of this log, starting where it says coefficients until there's no text is left. Once you copy that, then you open your original Excel sheet to the AcaStat Sheet tab and just paste directly into your sheet to the right of your input data. This is a good place to store both the input and the output. Now done with AcaStat. You can close it. I never save either the two files it prompts you for because you can always re-import it, and it just doesn't make sense to save them around. You can if you want, but I don't do it. In that file that you copied to your tab for AcaStat, the most important information is under the three constants, under the B coefficient column in the very first table. So those are the three constants. Be sure you get all the proper numbers, including the signs, pluses and minuses, because that makes a big difference. And the second one at the bottom of the screen is it summarizes the accuracy of the model. So you need to look at that as well to see what's going on. Next, you want to port this formula and model to an Excel spreadsheet. I'll give you a link later on to the spreadsheet for L193. And all you're going to do is plug those three coefficients in. Make sure the signs match, because sometimes they will actually flip around from positive to negative, but they're pretty consistent. The first one being negative, and the second one being positive, and the last one being negative. It shows up that way about 90% of the time, but not always. This assumes that the signature formula is located in column K, and that the signature distance from the signature is in column L. So what you do is you take those three numbers, and where it says constant in this formula, you just plug in the first constant, and then where it says sig, that's where you put in that number, and where it says genetic distance, you put in that coefficient. Now, it has all three of these twice because this is just one equation over on the numerator side. The denominator has 1 plus the same equation. So you got to do this twice. You could create another formula to do it once, but that's just probably not worth the effort. So being a statistical software package, it gives you a lot of information that you're probably not used to seeing. It gives you 4 kinds of prediction. First of all, it says if it's observed to be 0 and predicted to be 0, that's a correctly predicted negative tester. So that's the first one in the chart. And then there's observed 0 but predicted as 1. So that's a false positive because you observed it in real life as being converted to be 0, but the model is predicted to be 1. And then there's observed equals 1. That means it actually tested positive, but you got predicted to be negative for that, so that's a false negative. That's the most important one there because you want to see how often it doesn't correctly predict it positively. The last one is if it's observed to be 1 and predicted to be 1. This is how many testers that are actually being predicted correctly from the results. So another column is the last column of percentages, and where it says observed equals 1 on the end, it says percent correct. That shows you the accuracy of predicting positive in your model. False positives are important because they inform you where the model fails to predict negative testers as being negative and prediction is positive. So you really need to understand that there are 2 forms of false reports. So if you really want to go around and play with AcaStat, here's the URL to go to the AcaStat website and download your product for a mere $10 plus tax. And also to make sure that the formulas work, the formula can go anywhere, but K and L has to have the signature and genetic distance in those particular columns. Otherwise, you're going to modify the K and L to wherever the signature and genetic distance from the signature are located. And I gave you a link here to the actual analysis of L193, and you can see uh, the actual formula way out to the right, and then it will actually correctly evaluate and predict every single tester. And you'll have to copy and paste this, and that formula will update all the changes. The row number of the formula remain the same. So it's a very portable. Every time you add somebody, it updates. And if you want more detail on YSNP prediction and how it works, here's another YouTube video on YSNP prediction. Hope you enjoy this presentation, and I hope you really consider using AcaStat because it's a pretty neat tool.